let us move to the outline of the presentation. So first of all, I will introduce some of the key concepts that I will be using for the next part of the presentation. I will mainly discuss defects and traps, and then also the physical mechanisms that are inducing dynamic effects that then might be compromising the operation of the device or the integrity. So I will discuss here. I will be mostly focusing on the stability. I also talk about the reliability and failure, and also some words about breakdown as well. Then the main presentation is this part here, where I will show case studies on lateral GaN hands and also some on vertical GaN devices, the work that we have done with partners in the YESvGaN project. So I will show how we apply these concepts to study these kind of devices, and then I will conclude. Okay, so just a few introductory concepts. So, of course, the reliability is about studying how a device degrades over the operation time. So, of course, both there is a reduction in performance, which this could be related to the stability, and then a failure eventually occurs, so the device is no longer operable. And so just to distinguish these two, just to make it clear what I mean by this, the stability would be the recoverable changes in the electrical characteristics of the device. So even though you're, let's say, switching your device in a converter, for example, you might have a drift of the threshold voltage, as shown here, or also an increase in the on resistance, which both, of course, are undesirable effects and need to be understood and controlled to make sure that the device is performing as you expect from the specifics. But the important part is that no permanent device degradation is occurring, meaning that if you turn off your device or your circuit after some time, it will go back to the original specs. So this is not really something that is not recoverable, which is then what really the reliability is going into to study and understand. So these changes in the transistor characteristics will be permanent, or in the end you could also have damages that of course will make the device no longer useful. And of course there are many mechanisms that can lead to this kind of problems. So let's try and see if we can understand a little bit more about those. So these introductory concepts about defects and traps might be familiar to some of you. So this will be just a review, or maybe someone will also find this new or anyway useful. So defects from, let's say, a very simplified point of view, but just to give you an idea, are imperfection of the crystal that, of course, can then lead to the electrical degradation of the device. So, of course, there are many different types. I am just summarizing them here. So I will just then move to what I'm more interested in, which are traps, which are, let's say, sort of a subset of the defects that influence the electrical behavior. So, in general, we say that for these defects to be causing electrical, to be relevant from an electrical point of view, they need to be located in the forbidden band gap, so that they will exchange carriers between the conduction band or the Bayes band, depending where they are located. And of course, because GaN has a very wide band gap, you can also have a lot of traps. And of course, you have either the emission or capture of electrons, and also pulse. And both these can be relevant for gallium nitride devices. And I will show you why this is the case. So this movie, I can just say that traps are not located in the middle of the band gap, but they are maybe either closer to the coaxial band or to the venous band, because if they are in the middle, they really are not called traps, but rather recombination and generation centers, because the events of capturing either electrons and holes have the same probability. But I guess that in GaN it's less of a problem than in silicon. So of course there can be intrinsic defects and extrinsic ones. This would be related to some imperfections of the lattice of the crystal, as we discussed before. So you can have nitrogen or gallium vacancies, or you can also have interstitials or extended defect like dislocations. And for the extrinsic traps, I mean like impurities that are introduced during the epitaxial growth of the layers. And well, specifically, you also introduce either carbon or iron for reducing the conductivity of the buffer, as we heard in the presentation on Monday. Then magnesium is also widely used for realizing the p-type layers. So again, it is important to so the effects of these traps will be determined by where they are positioned in energy inside of the band gap. So unfortunately, what also complicates more the things is that a defect or a single impurity can also behave differently depending on the growth conditions. So it is also important to separate these. Let me mention that many of the concepts that are in this presentation can be found in this reference paper. So this is a tutorial paper that we published a couple of years back with some of the collaborators in the project, especially University of Padua. So if you're interested, I can refer you to this paper later. This is just to show you once again how many kinds of defects you can find in a gallium nitride device, and each of these can have influence on your electrical characteristics. So in principle, you would need to study and understand all of these, but of course maybe some are more relevant and some other are less relevant, in the sense that maybe they are already being taken care of during the development of the technology. Okay, so the whole database again is in this reference here. Once a little bit more about trapping, just to say that again, even we said that traps are a subset of defects, and even with traps, you might find some of them are not really influencing your device behavior, and so the traps that are really important are those that have relatively long capture or emission times, so that these will respond slowly compared to the charge up of the device. So just the ideal device capacitances. So in this case, while you're switching, you might be charging or discharging some other parasitic capacitance that will then affect the operation of the device. So this is just it. So they affected that after all, they just affect the dynamic device performance. So to understand a little bit better about the trapping mechanisms, it's common to do this kind of classification where you separate the traps based on their location or how they charge and discharge, and the type of mobile carriers that are actually involved, so either electrons or holes. So of course, if you are capturing electrons, that you will reduce the 2DAG here. So after all, your conductivity will be less, or either there can be emission of electrons, which can also, or could be also holes captured, which will instead increase the 2DAG conductivity. So both can happen, of course. So it's quite a wide picture and complicated because of all the traps that are inside of the device. So another important thing that I will be mentioning often is that it's common and it's useful to separate the effects based on the two of the main parameters, or let's say three, that is the threshold voltage, the ohm resistance, and the transconductance. So depending on where trapping takes place, these parameters will be affected more. So we say that in the gate-to-drain access region, which is normally the widest region in an electrical device, there it will be affected in terms of the access resistance and of course also the transconductance. And instead, if trapping occurs below the gate or near the gate to source region, it will be mostly influenced in terms of threshold voltage. So this is also a way to distinguish the traps that are active. Okay, so yeah, because here I mentioned the access resistance, of course, in a lateral device, this access resistance will be the one that will be limiting the R-on, because this, again, the LGD is just larger here than LG, so in the first approximation, this is what really determines the R-on. Instead, in a vertical device, this is a trench MOSFET. You can see that the thickest region or the longest region is the drift layer, so of course this will be the one that will be affecting R-on more. And one of the advantages, of course, is as you know, of the trend of the vertical devices is that because this drift region is below the critical region that will be the gate oxide, then trapping here likely will be more or less of a problem than in a lateral device. So here you have the advantage of more stability of the R-on. Of course, you then have other kinds of problems, but we will look into that a little bit later. Okay, just to summarize the trapping mechanisms based on their location. So this is for a lateral device, surface trap location or passivation. So let's say happening here. These kind of issues have been more or less solved by using good passivations. Of course, trapping can also happen in the Algan barrier that is separating the surface from the channel, or it can happen in the GaN buffer if you're using extrinsic impurities. If you have a mishap, like we seen yesterday, the gate insulator can also be a source for instability, or also the PGAN layer in PGAN amps. This is a popular option nowadays for normally off devices. So this will also cause some troubles that we will look into. Okay, so yeah, maybe this one I can skip because it's very, again, this can all be found here. I will be discussing just a subset of these effects, otherwise we'll stay here for the whole day, and then yeah. So this is maybe more interesting. That of course, since as I mentioned, there are many locations or carriers that can be involved into the trapping. You need different kinds of test conditions in order to separate these effects to try to understand something about them. So these will be the actual operating conditions. For example, for a converter where you're switching on and off. So of course it's important to let's say stress the device, so kind of accelerate the effect of trapping to see what could happen in a real application. And so basically this is all about going below threshold with the gate and then applying a large VDS between the gate and the drain and the source. And the opposite state, of course, will be something that the VGS is closer to the threshold voltage, and the VDS will be slightly positive. Okay, and but it's also useful these conditions, the negative and positive gate stress. So you will apply a negative voltage on the gate or a positive while keeping the VDS zero. So this way you can separate what is happening below the gate from what is happening also in the access region here. Okay, so this is just once again to illustrate how you can separate the effects by looking at the drift of the threshold voltage or the R-on, and of course also the the GaN by using different kind of test conditions, as I mentioned here. So again, what happens under the gate is the threshold, let's say, just so we have one concept clear, and what happens in the access region will affect the around and GaN. Okay, so once we understand the mechanisms, we look into what are called the trapping effects. So, or we could also think about it in the other way. I mean, starting from a device characteristics, you will see you can take some measurements and see that your device is behaving like the Bluetooth curves before you ever switched it. And after some switching, you can see that your Aron is increasing, and also your knee voltage is increasing, so your device is not behaving that well. So at this point, you wonder what is happening, and then you go through all the concepts that we already see. So you can see that this has been called the current collapse effect. So there are many ways to actually probe this. So, but here you can see what happens in gallium nitride amps with an ion doped buffer or C-doped buffer. So in either cases, you can find there is a relatively strong current collapse effect. And yeah, as we will see later, these effects are not really solvable in the sense that once you rely on this kind of doping to reduce the conductivity of the buffer, you will have this kind of trade-off because you will have some worsening of your dynamic performance. Okay, so yeah, this is very important effect, and it's a combination of also the threshold and the Aron increase. So it's important also to perform other kinds of tests to try to separate the two and see what traps are causing these effects. So a related effect to the current collapse would be the dynamic Aron increase. This is maybe more important than the previous one, because what happens is that if you are switching your device off, your Aron will be increased, or even if you cross some critical voltage, you will just see your device that is not working anymore. So of course, after all, this is one of the most important things, because you want a lower Aron to have a high current. So you need to keep this effect under control. I will come back to this later when I will explain something more about this kind of non-monotonic curves. The other major problem besides the Aron is the threshold voltage instability or IV isostasis, which are very much related. That you can see that after the application of negative or also positive voltage, you see that your threshold is basically changing very much. This was taken on gallium nitride MIS amps, so they had the gate insulator, so you can see that this kind of devices have this problem of instability of the gate stack. This instead of I think they are also MIS amps. So yeah, there's a lot to say, and I will come back to this as well. So yeah, these are also other effects that are somewhat, let's say, less important than the other ones. So I might just skip them. Okay, so we've seen a lot about trapping, which is more related to stability of the devices. So coming a little bit to the failure instead, as I mentioned before, the reliability is basically the time a device can perform within specs before failure happens, which is normally identified by let's say a threshold event. So for example, leakage exceeding a certain value, at that point you know that your device is not going to work, or it could catastrophically fail. So of course you want to avoid that case. So these pictures show what happens under ESD tests that are taken under different conditions in the off state or in the semi-on state. that you can see that your safe operating area, it's different depending on the conditions that you use. So you need to take this into account when you are designing the device for circuit operation. Okay, so also in this case there are many mechanisms. So why is this happening? Yeah, so looking, for example, to a failure mechanism happening in the on state. This is the TDDB. So this is something that comes from the silicon MOSFET CMOS devices. When you are applying a large positive voltage on the gate, your leakage at some point will be so high that your device will fail. And this can also be catastrophic event. So of course you need to keep well out of this zone. This is something that was shown for vertical trench MOSFET. You can see the electric field here. It is very high, even exceeding the critical field. So of course at this gate voltage, your device will fail much faster than in case you're applying lower gate voltage. And this can also happen, of course, for different reasons, but as in the PGAN NAND also, you have this region that is making your threshold positive, and if you cannot apply too much high gate voltage, because you will start having a very high gate leakage that eventually will cause something very similar to this that is taken on a miscent. So though here you don't really have an insulator, but you still have the problem of the leakage after you turn basically this junction on. So this also needs to be taken into account. And this is something that happens during the off state. Because you're applying very high VDS, the gate edge of your device, where you will see peaks of the electric fields, and we will also see in some other slides, would be very high and cause a failure of the passivation here. The passivation was what was causing the failure of the device. You can see here kind of a hole, and in this case the devices with second generation were having a different vertical structure, so the epi was changed in order to sort of ameliorate the field happening at the edge of the gate, so they could achieve a higher lifetime. So once again, there are different techniques also here to identify the mechanisms that are occurring, and you need to have a good knowledge of the device operation in order to understand which one is the layer that is going to kill you in the end. Another important mechanism that was studied some years back is this inverse piezoelectric aspect, where basically, so we mentioned that polarization charge will create the 2-lag because of the crystal structure. So basically, the way the atoms are arranged will give the polar charge. But we can also say that because of the charge, you can have a mechanical effect in reverse. So just by applying a voltage, you can cause some displacement. So of course, because these stacks are all one on top of the other, this will sort of stretch, and this might cause some defects here that will carry leakage currents. So this was shown very nicely here, that you can see that the graded devices were having much higher leakage currents because of the degradation caused by this inverse piezoelectric effect. And this is something intrinsic to the device because of the presence of the polar charges. So to complicate even more things, it's not only about looking at the on state or the off state. It's very important when you switch the device, you try to, instead of follow this kind of curve, you try to follow more like this kind of curve. So where you try to keep the current under control when you're switching. Otherwise, if this is not the case, you're probably likely going to excite hot electrons, so very energetic carriers that might overcome barriers and that might also trap, of course. And these will, well, besides the let's say the transient effects that you have high power dissipation during the switching, these can also lead to some degradation effects that can also be semi-permanent. So, of course, this is some kind of test condition because you will never go like this unless something is going wrong in the design. But it's important to do this as well, just to understand the limits and how how far you can go. Yeah, I realize these are a lot of concepts, but hopefully they will clarify the results that I will show later. So just a very few words about breakdown in the lateral devices. So you can be either limited by lateral effects or vertical effects, in the sense that lateral meaning mostly leakage happening either through the passivation or the surface, or happening between the source and the drain, so you have a current in the buffer. And instead the vertical component would be some kind of current that is going through the substrate instead. It could go like this, or it could also go like this. So if you are designing your device very well, you could say that the lateral components of the current, of the leakage currents, would be low, so you can increase your LGD to effectively increase the breakdown voltage, and then in the end your breakdown will be limited by the substrate current. And of course, if you want to go even higher, you will just go with the vertical MOSFETs. There are also some other tricks that you can use to increase the breakdown, as was discussed on Monday. So you can have few plates that are effectively increasing the pinch-off voltage here. So the electric field at the edge of the gate, which again is where the field will be mostly concentrated, can be spread out, so you can increase your breakdown effectively, and you can extend the concept to have multiple few plates. Or else you can change the epi stack, or you can do this that was already shown, that you remove the aluminum nitride layer and some of the substrate to sort of eliminate the most effective region, which is the aluminum nitride and silicon cert interface, so that you can go to much higher voltages. And this is to demonstrate that, again, if you take care of the lateral effects, so if your leakage current is under control, then you can go to very high breakdown voltages, at least in principle. Okay, so now I will come to the core of the presentation, which is the results that we have collected over the years. So this is about breakdown, so I was connecting to that I just shown. This is some devices from FPH some years ago. This is a lateral GaN hand with a C-doped buffer. You can see that in this case, increasing LGD increases your breakdown voltage. Yeah, here actually the voltage is in 1000 volts just because of the limitations of the system, but the point here is that this slope here is much less than the critical field of GaN. So the question would be why this is happening. So we try to understand that. We compare two different kinds of devices. One that had no extrinsic doping, so unintentionally doped buffer, which corresponds basically to this wafer A here, which has a lower threshold and a slightly higher current. Yeah, as you can see here from the band diagram, your Fermi level will be kind of close to the conduction band, so you will have a very high leakage. Instead, when you dope with carbon, which is why you do it. You move the Fermi level closer to the valence band. So this will basically become a weakly p-type region. So then in this case, your the buffer leakage will be suppressed, at least to some orders of magnitude. And what you will achieve is this: that basically you will be able to effectively modulate the electric field beneath the gate drain region. And by increasing the LGD, you will see your depletion region that is expanding. So this is the reason why the breakdown will increase with the spacing between the gate and the drain. Instead, if you have very high leakage, you basically don't have any depletion region here. So your field will just drop below the gate, and because of the gate leakage current, your breakdown field voltage will not change with the LGD. So it will just stay there. And we can see it here. These are compared to the measurements that the UED buffer will just increase the current very much at fixed voltage, so regardless of LGD. So VBR will just stay there. And instead in the CDOP buffer, because you decrease this leakage, you will see this slope happening that is in agreement with the measurements. So with the simulations, we could understand what is happening, and we could tell that it was actually the C doping that was giving this kind of effect. Okay, so this is taking one step further. When it comes to modeling, you need to look, of course, try to have let's say a resemblance of your actual device that is able to match the experiments from many angles. So meaning that you shouldn't try to just fit one result and then publish it, but you also should try to ask yourself if you can try and see if your simulation is in agreement with other effects that are related to what you're looking into, and so if it all is consistent. So this is what actually we tried to do. These are still measurements from the same paper, so we were lucky to see both the breakdown scaling and the current collapse here shown just as a decrease in the current. This is just one definition. So for the modeling, what is important regarding the C doping is that basically, as I mentioned, the main effect here is to shift the Fermi level closer to the valence band, because basically you're introducing sector traps that will sort of pin the Fermi level here. You will have also, though, a lesser concentration of donors that are coming into the band gap. This is, also in agreement with some DFT calculations. So this has also been debated for quite some time, how to properly model the carbon. But at least for a device point of view, this simplified model is able to, explain many features, many results. So we believe that it's sort of reasonable. So the main level would be 0.9 eV from the valence band, and the donors will be closer to the conduction band. But the important point here is that the concentration of acceptors will be always higher than the donors, and you can define a compensation ratio here that we will see has an influence on both these parameters. So you can determine what would be the concentration by combining the experiments. So you can see here the dependence on different compensation ratios. So basically what we did was to fix the acceptor concentration, then we varied the donors concentration to vary the compensation ratio for these three curves. Instead of one curve, you would change both to keep the compensation ratio fixed. Okay, so basically here the idea was to match both the results. And the important point was that to achieve this kind of fitting, you would need to conclude that the amount of carbon that is actually electrically active or giving you effects is less than what is the nominal doping that you're introducing. So apparently some of the impurities are not really going into these levels, so they are not giving you any electrical effects. Okay, so let's try to maybe go further a little bit. Okay, so let's move from breakdown and current collapse to this problem of the Aron. So dynamic Aron we discussed a little bit before. So these are experiments that show how your on resistance changes when you apply. This is off-state stress. So you apply large voltage on the drain terminal, and then you keep your device turned off, so below threshold, and you see that the on resistance is increasing, and this effect is accelerated by temperature. Sorry, and then also your recovery. So you're keeping then a very low voltage on both the gate and the drain is accelerated by temperature. So like this. Normally this is more conventional in the sense that the emission rate is dependent on temperature to the activation energy, which basically corresponds to the trap level, but instead the capture is not really activated. I mean, there is a temperature dependence of the thermal voltage, but it's not as high as this one here. So we tried to use the simulations to understand what was happening here. Yeah, very simply, so you can see here that we try to reproduce the experiments. In this case, we adopted a stress where we applied a negative voltage on the substrate, because basically from the electrical point of view is equivalent to keeping this below threshold and having a large voltage here, but makes the whole effects happening in the buffer more uniform. So it's easier to analyze. So what happens basically is because of the C doping, you have holes in the buffer, and these holes can move around and will give you some dynamic effects that are related to the amount of traps that will be ionized here close to the channel that will deplete the 2-deck after stress. So you see that basically this is a picture in the fresh condition, so before applying stress. So you have this is the depletion region between the buffer and the channel. So you have a high concentration of ionized traps, and this is the free hole profile. And you can see that basically by after stress, so applying a large voltage here, you're increasing the depletion region here. So what happens, of course, is that you will lose some electrons in the 2-deck because of charge balance, and as also the free holes will decrease because you're widening the depletion region. And where are these holes going? Well, because here you have a barrier, they cannot go below the nucleation layer, so they will just get stuck here. And you can see from the simulation that actually there's accumulation here of holes. So this dynamic effect is what is increasing the Aron. And luckily, because basically you're not losing any carrier, when you go back and apply recovery, your situation is restored. So this is like a very good example of stability, where you can see that by just waiting for some time. Well, of course, for the case of carbon, it's quite a long time, so this can be still a problem for the application. You can restore whatever you had in the beginning, so you can see that simulations match reasonably well the experiments. And this we attributed to carbon emission of holes, because we extracted the same activation energy from both processes. Because basically during stress you're emitting holes from traps here that get trapped here at the bottom of the buffer, and then during the recovery the opposite happens. So it's all about, so the main limiting factor here is the emission of holes. Talking about instead threshold voltage, this is the MISANT. So as it was mentioned yesterday, they have strong problems with the drift of the threshold. So in this case, we analyzed two different icing conditions. So let's say moderate stress and high stress. And we could see here in this case the NBTI effect, classical one. So the threshold voltage is decreasing when you apply a negative voltage, because basically you are emitting electrons from let's say pre-charged interface traps. But if you apply a very large negative voltage, this is basically somewhat similar to the off-state conditions again. Your buffer will also start to have an effect. So basically, you are attracting holes from the C-doped buffer to the gate stack, and these holes will recombine with electrons emitted from the gate terminal stack due to some leakage effects. So in the end, you will find with a larger voltage that you had at the beginning. So this is kind of an interesting effect that we could also measure and simulate with the TCAD to sort of give us more confidence on what was happening here. Going back to Aaron, these are devices from partners ST. They have a GaN layer in the gate stack, and we did this kind of measurements. And saw that by applying different VDS, so by switching off the device at different bias, you see first a increase in Aaron and then a decrease. And this is, of course, something that might be good because you're behaving better than here, but still you need to have an understanding of what is happening here. And this is not really something specific to our devices. It was measured by many other groups. And many other devices from different manufacturers. So basically, here the bottom line is that there is a generation mechanism occurring. In this case, we simulated impact ionization, that we used the same coefficients that we use for the breakdown simulations too. Again, some sort of consistency with other results. And we could see that in the simulations, because of the generation of holes, basically there was a recombination with the traps in the buffer that were passivating. So the Aaron was actually decreasing because the 2DEC was more populated than in, I don't know, like 100 volt compared to 500. Instead, the simulation shows clearly that if you don't account for any generation mechanism, then the negatively charged traps in the buffer will just continue to increase, and then consequently also your Aaron will decrease. So this is just the simulation showing this, that here the ionized trap concentration, the effective, is lower than in the case that without the impact ionization. So just confirming or explaining why this is happening. And maybe this I can skip for the sake of time. Yes. So so this is important to say that just to stress a little bit more about the emission of holes from C-traps. Like ambient temperature, you have times that exceed hundreds of seconds. So you need to wait for a long time for the buffer to get sort of an equilibrium condition. And if you're switching faster than this, you will see your device behaving differently. And these kind of measurements show that you can misinterpret your results if you don't wait enough for the buffer to become stable, so to reveal this kind of bell-shaped curve that we saw also earlier. So it's important that when you test your conditions, you always know a little bit about what's about the traps, because if you're not aware of what is the time response of these traps, you will end up with wrong conclusions. Okay, so this is that still same devices as previously, so the PGAN, but we were looking into another aspect of gate stress. So I mentioned that when you use the gate stress conditions, either positive or negative, you do that to sort of focus on the threshold voltage shift. But what happens with this kind of device, that you can also have an effect on, or a pretty huge effect on the alarm as well. So by just applying a positive or negative voltage on the gate, you can see that the alarm changes by up to 17%. And this has to do with the fact that this layer is effectively floating. Because the gate metal is, you have a Schottky contact here, and you actually want this to avoid too high leakage currents. But then here the potential is not well determined, so this will float around. So there can be some storage of charge that will eventually cause you this trouble here. So again, we simulated this to try and understand better what was happening, because it appears that you have quite long times even in this kind of experiment. So it is unreasonable to think about just holes floating around, because they would normally be much faster than this. So it appears that after all there are some traps in the barrier, likely a barrier that will sort of trap the holes, or meet the holes in this case, that will cause this increase in the RON or decrease in drain current. And you can see here the concentration of ionized traps that we simulated and put in the barrier. That this is the negatively charged traps that is increasing, so it correlates very well with the decrease in the current. Okay, so in this case it would be the whole leakage current that is limiting this effect, but also the trapping that is happening in the barrier. This work I submitted to this conference, and I will present it later in October. Just let me skip this. Let me say just a few words on this, because this is more related to the degradation. So I mentioned earlier in my presentation that if you excite hot electrons when you're switching, then what happens is that you can have some permanent or semi-permanent effects of degradation. And this is what it's all about. So basically here our colleagues in Padova performed this kind of measurements where you have off-state step stress. So basically you're measuring your IDBG after applying different stress voltages and see the accumulated stress effect. And also the same experiments done on state. So you're because you have a negative threshold voltage 0, you will be turned on. So with 0 volts on the gate and increasingly high voltage on the drain, you can see here a much higher degradation of both threshold and GM compared to the off-state stress. And this is an indication generally that what is happening is that you have hot electrons that are coming into the picture. Okay, so you can see here in the on-state stress here, it demonstrated very well that this is the electron density. We perform a simulation to take into account also highly energetic carriers, and you can see that this is in the off state, so 60 volts on the drain and 0 on the gate. There are a lot of carriers that are also getting into the buffer. So what happens here, because you have acceptors again, and they have a high energy, so they can basically overcome the barrier that is between the conduction band and the acceptors leaving the band gap. So this is the 2.5 or around 2.5 pair that is between this level and the conduction band. But unfortunately, then you will not recover, because there is no way the electrons will have enough energy to get this barrier overcome. So they will just stay in the traps. And this, if you just look into the experiments, you will just conclude that this is some permanent degradation mechanism. And you would not normally point to traps or to a pre-existing traps at least. So yeah, the simulations in this case tells us that no, instead it can be pre-existing traps. And we also performed some UV light experiments to see if we had easily recovered this, and to a very high extent we basically recovered the whole of this permanent damage. So that also pointed to the fact that it was traps and not another kind of degradation mechanisms. So finally, I am almost done. I will just show some of the results that we are publishing with partners of the YESvGaN project. We did this work on MOSCAPs, pseudo-vertical MOSCAPs realized by FBH. So basically here you have the gate contact on top. So this is not really what the final structure will look like. But this is a test structure that is interesting to understand the stability of this interface and the outside as well. So they took these CV measurements, and they could see that by changing, let's say, sort of a stress bias, they could see many effects or many features in this experimental curves of the CV. The most important one would be this positive shift of the threshold, because this is what will be a problem in the actual application. So basically you can see that by applying a positive voltage here, that you will charge some traps likely, and then you will see a shift of the let's say threshold a little bit. Here you cannot really define threshold. And there are also other features that we were able to simulate and reproduce. Our approach was to sort of starting from the ET distribution that was extracted experimentally by comparing the different slopes of the CV curves after different quiescent bias. We could basically reproduce all of the features that they measured on the samples, and we could also, and we did this kind of analysis to separate the effects. We thought that it would be nice to see that different components, of course these are boxes and are simplified distributions to reproduce the experimental data, but they were good enough to sort of see this difference, that by turning off each of the distribution at a time, meaning you set the concentration to 0, you can see that different features were not reproduced. For example, here you did not have the shift forward of the CV, because basically the acceptor traps in the oxide were not there, so you did not see this kind of effect. And yeah, still we also did some simulation of the trench MOSFET from the devices of Bosch. So these are two kinds of devices with a different deposition temperature for the silicon dioxide. They also had a different processing, but let me just focus on the gate oxide for the time being. You can see that there is a huge hysteresis in this case, meaning that your threshold will be higher when you perform a backward sweep or your IDVG. So basically there is some trap happening in this device that is also proportional to the maximum applied gate voltage. You can see also that the current is somewhat low. Here in the second device it's much higher, but likely due to mobility reduction, but also pinning of the Fermi level likely. And here, yeah, instead you see a much lower isostasis. Although it's still present, but this kind of process was effective in reducing traps in the gate stack. So at the end, you get a lower hysteresis, which is proportional to the traps inside of the gate oxide. I will not be able to explain in detail why this is the case, but you can see that with simulations we were able to sort of match to a certain degree the experimental results, and this allowed us to sort of extrapolate what would be the trend by further reducing the traps in the oxide or at the interface. And so yeah, this is what we have done so far. Hopefully we also do something more in the next year or so of the project. So yeah, this was all I had. I hope that you had a nice overview of what the problems of HEMS can be. Of course, there are many. So the important point is that for the successful development so far, but also in the future, it is very important to try to do this work of separating the effects, trying to devise different tests to analyze them separately, and this will also very likely allow to have the successful development of vertical GaN devices in the same way that the lateral HEMS was possible. So, okay, thank you for your attention.
Gotcha.